you. So welcome everyone. We continue today with semi-simple categories, and then I will also talk about adjoint functors. But before we start with that, I come back to questions that Sebastian had last week concerning the direct summing group category of groups. Let me first actually I reproduced that what I told you was almost everything taken from NLab. If you look there at direct plus sum. And there's one more information from there which I want to share first, namely, in addition to the direct sum, there's another concept which one sometimes needs. We will not need it as far as I can tell. This is called the weak direct product. And I do not describe it in detail. If you know what a directed system is, then it will be easy for you. So we start by looking at the product, I and some index set AI. And no, call this E, just some other letter, where now we say that E, we let this vary over finite subsets of the total index set I that we have. And this is, of course, of interest when I is infinite. And this is maybe the main point here. When as long we have a finite direct product, then there is nothing to do with it. And then one can check that this gives a directed system. And so we can regard this as a huge diagram. And then this weak product over I and I of AI is what is called a directed colimit of that directed system. So since we probably will not need this, or almost certainly not need this, I put in brackets, but I mention it because for the category of groups and also for the category of abelian groups, this weak product is the same as the direct sum. So we could describe the direct sum this way. Another possibility is that we say that the direct sum is described as the subgroup of some GI now in group, the subgroup of the form. We have sequences of group elements, GI in capital GI, such that GI equals E, or maybe I should write EI, so the unit of the group GI for all but finitely many EI. And that means, in particular, if I is finite, then the direct sum is the same as the direct product. And then I made a statement that somehow the direct sum lies between the product and the co-product. And I have taken over this literally from NLab, but I cannot say more about it. It's really, I would say it's certainly closer to the product because of this property. And then you had this came up because it says, but if I remember correctly, but the category of groups doesn't have a zero object.
It's not.
Which is not true. It has a zero object.
No, it's not.
It's not additive, but it does have a zero object. This is not the same thing. Actually, the zero object in category groups is just the one element group.
Yeah, so it's not
And what also we did not require for direct sum, we did not require existence of zero object. We required existence of zero morphism. Now, if you have a zero object, then of course for any two objects, you have a unique morphism here and a unique morphism here. So you get a zero morphism between any two objects. So if you have zero object, that is automatic, but you can have also categories with zero morphisms without having a zero object. And I cannot give you a good example for that. I didn't think about it.
So we don't need to assume identity.
We don't assume additivity. Assume precisely what I wrote down. Existence of certain limits and coordinates.
Nice.
And of zero morphisms. And then a remark which I don't write down. If you search for direct sum for groups, then sometimes in context where people are not thinking of general categories, but just really about groups or maybe abelian groups, they often think of the direct sum and the product as the same thing. So they have to be a bit careful. Okay, back to semi-simple categories. We defined what a simple object is in an abelian category, namely an object which has precisely two subobjects, itself and zero. And then a semi-simple object is a finite direct sum of simples, and a semi-simple category is an abelian category with where every object is a direct sum of simples, and if there is a finite number of simple objects up to isomorphism, we call it a finitely simple. And here, next thing is a small remark. Right, as I already said, we can define C in more generality, not semi-simple in more generality than for abelian categories. And the most general situation that I have seen is the following. Assume C has a zero object. Nothing else required. Of course, C should be a category. Then we say a simple object. Again, call it S. Is an object which has precisely two quotient objects. And remember, for the definition of quotient objects, we actually didn't require anything, except that we have to say in general, it's not clear whether they will exist, but in this situation they do. And just F0 and S. And also, if C is additive, so it doesn't apply here, then this amounts to, or equivalently, we can say that just well, S is not the zero object, and for any object Y, X, and apimorphism from S, let's call it phi, to X. Either we have X equals 0 or phi is an isomorphism. It's just a reformulation there. And there is another, well, there's something in between here where you can define simple objects as follows. If you have a zero object and you have different cokernels, then you can define simple to be that for every difference co-kernel diagram of the form here, where this is phi. Phi is either 0 or an isomorphism. So that, but this is maybe not so important. But the fact that we deal with quotient objects here, this is actually relevant because in the following, if we in the category of groups, we do have direct sums, and we have the notion also of a simple object, because there is a zero object, and that's the only thing we need for this definition. And assuming we use, there is the notion of simple group. Do you remember that? Yeah. No normal subgroups, but if you look at sub-objects in the category of groups, then these are just subgroups. So if you would use sub-objects to try to define simple objects, then a simple group will not be a simple object, but a simple group is the same as a simple object in this sense. In a normal subgroup, when you use quotients. Let me also mention, without writing anything down, that later on, at some point or some points, we will actually, instead of working with categories, at least mention something we call a supercategory. And also in a supercategory, there's a notion of simple object, but it's not the same thing.
So you have two notions of simple object.
It depends on how you look at it. You can say a group is not additive, so I cannot use the definition of simple object I gave on Tuesday. But it has a zero object, therefore I can use this definition. You could. You could, if you could still, by chance, so to say, try a definition where you say subgroup here. Then you would describe sub-object here. Then you would describe subgroups, and then you would have a concept of simple object, but it's not so interesting because. You know that the notion from structured theory groups that simple group in this sense, normal subgroups is a relevant notion. Again, now follow some statements, mainly. Statements you know in one form or the other already, which are valid for linear categories, which the first one is Schur's lemma. Actually, I take two parts. One where I say C is abelian. And then the statement is that any non-zero morphism between simple objects is either an isomorphism or it is an isomorphism. So any morphism is either zero or an isomorphism. And if we assume in addition that C is k-linear abelian, K-linear and abelian, and also the Hom vector spaces then for any two objects x and y are finite dimensional. Then we have the statement that for any simple object x, say, in C, if you look at the endomorphisms in C, then this vector space is K division algebra. And here K is an arbitrary field. In most, as I said at least twice before, usually I will assume it's algebraically closed, and in that case, the statement is that the endomorphisms are isomorphic to K. And maybe A and B, just a sketch of the proof for A. Assume we have x and x prime simple objects, and we have a morphism F between them. Since C is abelian, F has a kernel. So we can look at the resulting morphism from the kernel of F to x prime. Let's call it H. Now x prime is simple. And H from the definition is a monomorphism. And from this it follows that either the kernel of F must be 0 or H is an isomorphism. And then you look at these two cases separately. Assume the kernel is 0, then it follows that F itself is a monomorphism. And well, for that you have to argue a bit, and then you use that X is simple to see that a monomorphism must either be an isomorphism or 0. And for B, no, for the second possibility that H is an isomorphism, from this it follows that H, because H composed with F has to be 0. No, if that is 0, it implies that F is 0, and if you put this together, you get a statement. And for part B, let me just write linear algebra. You use the fact that let's first assume K is algebraically closed. Then you know that for any linear endomorphism of a finite dimensional, which we assume vector space has an eigen value, and then you look at F minus eigenvalue times identity and apply part A. And then you have to extend this to the case where K is, when we have to see what happens when K is not algebraic. The second important result is the Jordan-Helder theorem. For that, we need the following concept, which actually we have used in the definition of locally finite category. It was 136, and I told you at that point that I have to provide you with this definition. We say we have X is an object X is of finite length. E is still abelian. then this means by definition that there is a finite sequence of objects that call this x0, x1, x2, up to some xn, and xn is equal to x, and x0 is equal to 0. And then we have inclusions here, so there are monomorphisms between them. We call this also filtration of x. Such that, so not just any, but it should have the property that if you look at a quotient object, xj divided by xj minus 1, then this is simple for all j from, let me see, 1 to n. And we call this, in this situation, we call this a Jordan-Hölder series. For the object, or of the object x. And we also say that the terminology we say that a simple object y appears in a Jordan-Hölder series Ly times, or one also says that it has multiplicity Ly in X if and only if Ly is the number of times that a quotient object here is isomorphic to Y for some j. And then there is a theorem. Let me see, maybe I write this here. Or Jordan-Hölder theorem. Which says that assume X is an object of finite length. Then every filtration, so every sequence of this type of X can be refined to a Jordan-Hölder series. So take such a sequence, then the quotients need not be simple, but we can just insert intermediate objects such that the quotients, the new quotients are simple. And also any two Jordan-Hölder series of the object X contain any simple object contain, meaning in this sense here, simple object Y with the same multiplicity. Meaning, of course, up to isomorphism and up to ordering of these quotients, we always have the same simple objects. And in particular, we need to, the series have the same number of terms. Then, of course, not surprisingly, you call this number n, like here, and then you say that this is the length of the object x.
You assume C to be abelian. Yeah. You have to state it.
I have defined x for abelian categories, and so
because this term is true for a group also, the group is not abelian category. It should be true for something more general than abelian category.
it certainly holds in more generality, but I cannot. I would have to look that up. But I would have to find it. Probably. Let me check. And then a third theorem, first lemma, Jordan Bölder, maybe I can put it here. It's the Kohl-Schmidt theorem. For that, we need the following concept. A definition. An indecomposable object in an abelian category is an object that cannot be written as a non-trivial direct sum. So it does not admit decomposition. A non-trivial decomposition into a direct sum of sub-objects. Of course, I can write every object as a direct sum of 0 in itself, but apart from that, well, many zeros in itself. And now the theorem says the step was too large here. That should not be a 7. That should be a 2. And then we have 163. This is the statement. The decomposition of an object of finite length remember, I defined this only for abelian, so here is you again abelian into a direct sum of indecomposables. Is unique up to isomorphism. So if I write an object in two ways as a direct sum of indecomposables, I will have the same up to ordering and isomorphism. And then a concept which we will not really use now, but very much later on, and now we need to have some notation, is the Grothendieck group of an abelian category. By GR of C. This is the free abelian group generated by the isomorphism classes of simple objects. I take the isomorphism classes and take formal sums of them and identify them if they have the same terms. And then I will use the following notation. Before that, I can use this part here. I write lambda, or if I have to tell, if I deal several categories, lambda of C for the set of isomorphism classes of simple objects. And I say set here, so I'm assuming here that the category is essentially small. And this is really a set. And for the elements in lambda, I use a small lambda or similar letters. So I write this, for example, like that. And then we choose a representative, which I will denote hopefully consistently by y lambda for each of these, for each of the classes lambda. And then we have the following simple observation. Lemma. The class, which we denote by rectangular brackets in the Grothendieck group of some object X is the following: the sum over all elements of the set lambda, and then has some coefficients which relate x to y lambda times y lambda, no, times lambda, where this here is just a multiplicity of y lambda in Jordan-Hölder series for x. So I take the Holder series. I take these quotients, which are all simple, and then they're relevant, the corresponding classes in capital lambda, and this gives me the class of X. And in particular, well, actually, it's not hard to check from this. It follows that assume we have a short exact sequence. No, I've used notation as before. In an abelian category with objects S, X, and Q, then the class of X in the Grothendieck group is just the sum of the classes of S and Q. Sum, I implicitly used it before. We write the group product additively. And up to this point, there were various statements now where I assume it's abelian, but we are in a section about semisimple categories. Now I specified the semisimple, and yeah, this fits here. Another lemma. Now let's assume that C is abelian and semisimple, or semisimple abelian, maybe better. Yeah, I should say the other way around because I don't have much. Otherwise, we have the following statement that every subobject is also a quotient object. And the other way around. There's no need to distinguish between them. That means in a large part of the physics literature, one only works with semisimple categories. You will not find the term quotient object anywhere. And thus also retract in the sense that we defined in 1.16. And remember that we defined that after introducing the notion of split AP and split monomorphism. This can be reformulated here by saying that in a semisimple abelian category, every monomorphism is split and every epimorphism is split. And this allows one to reduce various statements about arbitrary objects in a semisimple abelian category to statements about simple objects. We simply describe every object as a direct sum of simples. Then we make statements about simple objects, and then we put this together. And for putting it together, we have the we need some nice notation, and that notation I now introduce. Well, actually, I formulate it as a lemma, but it's more or less just notation. So again, C is semisimple abelian. And then assume we have any object X in C. Then there are monomorphisms which I denote by I lambda j, and in principle there is dependent on x, of course, but I suppress this, which are morphisms from y lambda, so simple object that I have chosen in the isomorphism class lambda to x, and lambda is an element in the set of isomorphism classes, and j is an element in some finite set, which I call maybe capital J lambda. Depends on lambda, finite. Coming from the fact that we deal with finite direct sums, and epimorphisms, which I denote by R lambda J. Again, also clearly depending on x, which go from x to y lambda, such that we have the following. First of all, if we first go from y lambda to x, and then from x to y lambda prime, we get the following: R lambda j composed with I lambda prime j prime. Then we get 0, except if lambda is lambda prime and j is j prime, and in that case we get the identity on y lambda. And furthermore, the identity on x can be written as a sum over all isomorphism classes, sum over all j's in each of these finite subsets, and then composition of I lambda j with R lambda j. And as you can check, this morphism here, which I denote by P lambda j, this is an idempotent, simply because if I compose this with itself, then I have I composed with R, composed with I, composed with R, and then in the middle R composed with I is the identity. And more generally, it follows from this, if I take two of these idempotents and compose them, then I get 0 unless they are equal. So one says these are mutually orthogonal idempotents. And this is not really a lemma, it's just a rewriting of things that I have said before. And there are still 2 minutes, so I can actually introduce some further graphical calculus. We will not use this now, but maybe at some point later on. For these particular morphisms here, I use the following notation. For I lambda j, I denote as follows. So remember, this goes from y lambda to x. So I would here just write lambda and j. And for R lambda j, I take the triangle. So in general, we have these coupons. Remember, they just stand for points. They are just 0-dimensional, but in order to visualize them, we have some special symbol, these coupons, and for these particular isomorphisms, I use particular conformals. And then P lambda J is, of course, just I after R. So I can just put them together here, but because it's faster to draw, I will draw it like that. So this will be from lambda J to from X to X. And then the property here says that if I have such a decomposition, if they are equal, so lambda J, then I can just leave this out and get something which is the identity, and otherwise I get 0. Okay, good. Going to stop. And after the break, I will say a little bit more about idempotence, also in the situation where the category is not necessarily simple. Should we stop here? So, as I said, we are often interested in morphisms which are idempotent, also, or even in particular in situations where the category is not semi-simple. And the first definition I need here is the following. We say that an endomorphism, say P in X, C some category, X some object, you don't assume more, is called split idempotent. If and only if there exists morphisms I and R analogous to what we have here. There exists an object Y in C, a morphism I from Y to X, and a morphism R from X to Y, where I is a monomorphism and R is an epimorphism, such that when I compose them, I get P. And if I compose them in the other order, then I get the identity on this additional object Y. First observation. The terminology makes sense, namely if P is a split idempotent, then it's an idempotent. By the same simple calculation that I mentioned before, if I take P composed with P, I have I composed with R composed with I, which is the identity composed with R. I get that. So, Now a lemma where we assume that we are in an abelian category. C, assume C abelian, and P, say from X to X, an idempotent. Then it follows that the identity of X minus P is also an idempotent. And a further statement, if R doesn't make sense precisely in the way that no, yes. Assume that R is not an arbitrary, well, there is an R which is a section of the morphism which I call Q. I used a different notation before, unfortunately, in an exact sequence. Take this as 0 as X Q, short exact sequence, and I call this I, and this I now call Q. And section means that there is a morphism R in this direction, such that I and R, I after R is an idempotent. No, sorry, that doesn't make sense. R after Q is the identity on X. But no, Q after R is the identity on Q. In this case, then also if we call I was mixing up notation here. So we need now P, which should be R after Q. So I was confused with using this. I don't need this here. Actually, then not only P because of this identity here, it's an idempotent is split idempotent, but also this other identity. It should be. No, identity on X minus this P is also split. It's an idempotent in general, but it's split, and the first part is just writing out identity of X minus P composed of itself, and using the fact that P is an idempotent, and in the proof of this, I need this morphism here and show that actually in this situation I have a retract here, and then one proves using that C is abelian, that also here one has a retract. And then from this, one can deduce the statements. And then a lemma, or maybe more remark. Splitting of an idempotent P, assuming it exists. So these morphisms, this object Y and the morphisms I and R, this both the limit and the co-limit of the following diagram. I just take two parallel arrows from X to itself. One is P and the other one is the identity. Now, whether idempotents are split or not is an important issue. And then in particular, one defines a category is called idempotent complete. Or also Karoubian. If and only if every idempotent in C splits. And there are many categories which are not idempotent complete, but there is a universal construction of completing with respect to idempotents, and this is called idempotent completion. Or also Karoubification of a category, denoted by car of C. Of C. This is the following category. Well, one can formulate it as by saying it's the free completion of C under split idempotents. So one simply one takes a category which contains the original C and in which all the idempotents are split, and takes it as small as possible. And what does this mean concretely? Well, exercise describe this in full detail and show that I will give some details. Show that the Karoubian completion of C is equal to C if and only if C is Karoubian. Let me write Karoubian a bit shorter than idempotent complete. And in particular, what we have is that if we have an object, let's call it X in the Karoubian completion, then this can be expressed as a pair consisting of an object in C and P in the endomorphisms of X and idempotent. And then in particular, the identity morphism on X hat is just P. And a remark, which is maybe slightly mysterious, because I use something which I will notify now, and think if there's time, I will define it sometime in the future, but maybe there's not time, is the following. Remark. For ordinary categories, meaning set enriched. So morphism sets are just sets and not something else. Idempotent completion. Is the same as what is called Cauchy completion. But I don't tell you what it is. So there's a concept which you have in enriched category theory, which in the setting in which you are part of the time in any case, maybe just ordinary categories with morphism sets being sets, then it's just idempotent completion. And then maybe I also should point out that in particular every semi-simple category is idempotent complete, simply because there is lemma every idempotent splits in thing. You can do this by hand by just writing X as a direct sum, decomposing the morphism space into a direct sum vector space between simples and morphism sets between simples. But it's a set enriched case, not direct sum, but I will. But yeah, it's so when we have and no, that was not what I wanted to say. If no, I don't make a statement because I'm now not sure about it. For the rest of more or less the rest of this section about semi-simple categories, which is not only about semi-simple ones, I want to take up the distinction between simple object in the way we have defined now, and the notion of linear simple or absolutely simple, which we mentioned in the context of linear categories.
Just a question. Why is the Categorical completion?
Because then you need to look at an idempotent in the morphism space. I didn't describe the morphism space. So you have to. If I didn't write it down, maybe I should add this. The morphism spaces of in the completion between X, P and Y, P prime is a certain subset of the set of morphism from X to Y, compatible with composition with P and P prime. And if you use that, you can analyze what are the well, if you write out the definition of idempotent and use this, then you can see that, that this more or less gives you a splitting of the idempotent. But I don't want to write it down now because I haven't done it in preparation. Probably need a little bit of time in order not to make it. Assume now for the rest of this section that C is k-linear, well, until further notice. And then we have this notion of absolutely simple, or I prefer linear simple object. And assume that it's in addition also abelian. Then we have the notion of simple object. And you can ask how are they related? Let me first, this will need some time because they're not the same concept. We can have objects which are linear simple but not simple, and we can have objects which are simple but not linear simple. And because of that, I introduce a new concept, a new terminology. It's not really, anyhow called a definition. And I'm not sure, I don't think this is used very often. I say a relatively simple object is an object which is simple but not linear simple. And as a nice source of such objects, if I look at the category of modules or some algebra in a monoid category, which we will do in section 2, then there is a notion of induced module, and certain induced modules will be simple in the sense, well, the categorian is not necessarily abelian, but we can use simple in this more general sense that I mentioned, using subobjects, and an example, but they are not linearly simple, and an example of that are what is nowadays called Majorana objects, or also type Q objects in applications. So completely when you deal with fermionic topological basis of matter. So I now have two statements, one in one direction, one in the other direction, about the relation. Well, a statement about when one of these properties implies the other. And I am not absolutely sure that it's the most general statement one can make, but I think it's at least very close. So one of them is the following. Lemma assume C is k-linear. With a zero object, and assume that every monomorphism in C splits. Then one has the implication that if X in C is linear simple, then it's also simple. And I think this is probably can be found in the literature at various places, but I haven't seen a full proof of it. Therefore, I want to go into some detail here, and I assume I will prove the converse of that. I assume that X is not simple, and then show that it's not linear simple. Now, if it's not simple, by definition, there exists proper sub-object, and I assume here that I have defined sub-objects via define simple via sub-object. So I should better say then there is a proper, so not equal to 0 and not equal to itself, a sub-object, call it S. And now, since every monomorphism is split by assumption, it follows that there exists an epimorphism. Let's call it R in the other direction. Such that by splitting R composed with I is equal to the identity on S. And that means that P defined as I composed with R is an idempotent. And then we show first that P is not 0. And this is because since I is is by a construction a monomorphism, it follows that assume I composed with R, which is P, would be 0, then it follows, because this is mono, we can conclude from that R is equal to 0, but this is clearly in contradiction with R composed with I being the identity. And also P is not the identity, because P equals identity would easily imply that I is an isomorphism, in contrast to the assumption that this is a proper subobject. And now suppose X is linearly simple, linear simple. So we show that this is not true, so then we must get a contradiction for that. Well, what does that mean? P is an idempotent in the endomorphisms of X, but the endomorphisms of X would then just be one-dimensional. So this would be some number psi times the identity of X. And then P is an idempotent, so psi squared is equal to psi. This has two solutions, psi equal to 0, which is excluded, and psi equal to 1, which is also excluded. So the assumption is wrong. This assumption is wrong, and therefore we conclude that X is not a linear simple. And this gives the result. In the case that C is not just k-linear abelian, but in addition also semi-simple. Then there is a simpler proof. Maybe I don't write this down. I'm going to say it in words. If we again assume X is not simple, if the category is semi-simple, this means it's a non-trivial direct sum. So we can, in the case that C is abelian, we can write X equals S plus Q, where both of them are non-trivial. And
in the case C, it's simple.
Thank you. Where both of them are non-zero, and then there are corresponding idempotents PS and PQ in the endomorphisms of X, and then one shows that the endomorphisms contain K PS plus K PQ. So they are not just multiples of the identity. The other direction is as follows. So C is k-linear, of course, otherwise there's nothing to be discussed. And we also assume abelian again. And we assume that K is algebraically closed. You see why this is needed. Then, in this situation, we have the other direction, X simple. Extremely simple. And there is something wrong here. I have to look that up. One does not really assume abelian because otherwise zero object would not be an assumption. And where did I say abelian? Because I use this definition. I have to check this out. Actually, I didn't realize this. Yes. So coming back to the point here, if we have an abelian k-linear category and K is algebraically closed, abelian means in particular there are zero objects, and yeah, then we need that monomorphic split. If we have that, then the two concepts are equivalent. And how does one prove this? Again, the other direct, the converse statement, assume X is not linearly simple. That means there is some morphism, call it phi, in the endomorphisms of X, which is not the multiple of the identity. And then we set A to be the This is a vector space, but under composition it's also an associative algebra. And we define A to be the subalgebra, which by construction is commutative. Which is generated by the identity and by phi. Now, again, suppose X would be simple. And then, because C is abelian, it follows by Schur's lemma that that's where algebraically closed comes in. That A must be a field. Well, by Schur's lemma, it must be in the algebraic, by Schur's lemma, it must be a field extension of K. But K is algebraically closed, and therefore we see that A has to be K, and this is again a contradiction to, well, isomorphic to K, to be precise, and this is a contradiction to the existence of such a phi. So we see that X is not simple, and therefore X being not linear simple applies X not simple. Then we have this statement. And when C is not abelian, then we cannot apply Schur's lemma. And if K is not algebraically closed, in the abelian case, then we cannot use here. So in general, this is not. And let me give an example or non-example. Counter, no, not a counter example. Let me just have an example of an object that is linear simple but not simple. A non-simple Lemma module. In the representation category of some Kac-Moody algebra G. If you know what a Lemma module is, you will easily understand this. If you don't know, then just ignore it. When there are Lemma module you get starting from one element, highest weight state, and you get all the rest. And because of that, all the endomorphisms are determined by, all the endomorphisms compatible with the action of the Lie algebra are determined by what happens to the highest weight state, and therefore they are linear simple. And in general, they have non-trivial subobjects.
It's not so easy. Assumption which is not satisfied in this example.
But in that case, the category is still linear and abelian. And we can take K to be C, for example. And then we have such. Let me see.
So remember, right?
So we if it were we can if it's simple, then it will be linear simple, but we can have linear simple without base.
I guess this schema is failed.
Here, we see there must be something must not apply here, and we do have a zero object, but it's this property. Then a remark which is not important for us, but I think it's nice to know that we have defined, and we will only use the notion of semi-simplicity in the setting of abelian categories, but one can define it also beyond abelian categories. And this goes as follows. If we assume that we have a k-linear category, but not necessarily abelian, we call it semi-simple if still the following is true. C has direct sums. C is idempotent complete. And there is a collection of objects which are linear simple. I call them Z with some index L, or L in some index Z, with the property that if I look at the morphisms between Z and ZL prime, then if L is equal to M prime, by assumption this is just K, but K times the identity on ZL. And if L is different from L prime, it's 0. And we assume that these dominate every morphism space, let's say on XY, in the same sense as simple objects dominate morphism spaces in the abelian case, namely we have these such morphisms R and I, so there is a replacement of the role of simple objects. And the following is concerning literature. On abelian semi-simple. Abelian and semi-simple both. There is, of course, a lot of this in the book by Ettinghoff et al. And if you want to know precisely where, you can look at section 6.2 of a paper by Gu, no, PhD thesis by Gu, which is in the list of references, which now should be on the website. Okay. There are still 2 minutes. Not enough to really start something, well, not new, but completing the 110 here, but maybe saying some words concerning physics. Semi-simple categories, as we have seen, are very, very special. In the physics literature, in many contexts, you only are interested in semi-simple categories. For example, in one of your papers, you will find a formulation. Physically interesting theories are semi-simple categories. And to some extent, it is perfectly correct, but to some other extent, it's actually not. There are situations where we might be interested in non-semi-simple categories, also in application to physics. Typically, the more fundamental the system is, the more likely it is that it's that the category is semi-simple. But we can, for example, look at driven systems, where some external forces or more generally systems in interaction with some environment and often called open systems or systems out of thermal equilibrium. And then more generally, very often the situations for which you use category theory in physics are some idealizations. As soon as you have really realistic systems, like a condensed matter system, you typically make, or often make statements which are valid in the thermodynamic limit, but a real system in real life always is finite. Then when you should not be surprised if there are corrections for which you have to go away from. Okay, and now we can stop, and then I say more about semi-simple categories after the break.
So we wonder whether the previous algebra object form an avail category. But in fact, the group.
He had asked me this question, and I wanted to look it up, and I didn't have time, or I forgot about it. I wanted to do this just before lunch, but then something else came up, and but it's on my list. I don't see a reason why it should not be, assuming of course it's simple. It's brilliant.
Group is not a legend. For you, more or less,
that is correct. So, but the category. Let's first do it in the classical case. So just for Venus algebra field, the category of those is a subcategory of vector spaces. No, but let me see. Maybe this doesn't have. It's not a full subcategory, and therefore probably it doesn't have. So we visualize an animal. No, but there is certainly a starting point, because of course we can look at Frobenius algebras in a monoidal category, which itself is not a Debian, and then this will almost certainly not be a Debian. So it depends on the ground category of this category. It must follow from, if it's true, from with the help of the fact that one. So one has to go through this, preferably not the definition I gave, but there is translating this explicitly in every there are kernels and co-kernels, and these statements are one-line nifimorphisms, and for all of these, if the original category is abelian, then we know in the class or set of all relevant morphisms, you have these things, and then we have to check whether the kernel of morphism of Frobenius algorithms, just regarded as a morphism of the category, is still a morphism of Frobenius algorithms. So that it's not only kernel in the C, but it's kernel in the subcategory. And as I already told you, I don't think this is extremely difficult, but it's certainly not trivial. And I would prefer to statement. Well, I mean, to sort it out myself, or at least something about it. Somehow, I expect, we have to continue. I expect that it is for the simple reason that if it weren't, it would be likely that we find that statement somewhere. Yeah. So now we come to the last part of section 110, and let me just call the number here 187A, from which you can see that originally I had not planned to include this, but at some point I realized that it does make sense to do it, and this is precisely concerning the motivation for many physicists to restrict attention only to semi-simple categories. The keyword here is unitarity. In quantum physics, you deal with statements about probabilities, and they typically evolve in time, but there are certain probabilities, such a total probability of a particle being there, which should not change in time, and therefore the transformations you should you make in time to your system have to preserve this, and in terms of operators on Hilbert spaces, this means that the operators have to be unitary. And I don't want to go in any details about Hilbert spaces. Actually, I will mention one statement about Hilbert spaces a bit later on. But in any case, it makes sense that there are good reasons to look at categories which are unitary in a physical sense, and under very mild conditions, both in quantum physics and then also here, from unitarity will imply symmetry. And I will not go into that. I'll give you the definition, the relevant definition, and this is well, actually there are also other names for this, but I will use this C star category, and relevant literature here I can mention is a paper by Galindo. I think this is already in the list. If not, it will be in the next version. And there is also a paper by Selinger or Sillinger, which is about graphical calculus. But in section 4.7, there is a particular discussion of these categories. So what is this? It's a linear category, but not an arbitrary field, but complex numbers. And it's endowed with an Ender functor, which is denoted by star or sometimes by the dagger symbol you have in quantum mechanics. And not really an Ender functor, it goes from C to as the opposite, so a conformal interfunction, you could say, such that this is which is antilinear. And I don't want to define that. If you don't know what it is, you can look it up. It's very simple and involutive. So star composed with star is the identity. And also is the identity on objects. Identity on objects. So star of f, which one just writes x star is the same as x for all objects. And if one just has this, that I should mention maybe directly, this is sometimes called dagger category. And again, there are also other names for that. And in order that it's a C-star category, we need in addition that each morphism space in C has a natural structure of a Hilbert space. Now, in the setting, we are usually all our morphism spaces are finite dimensional. So this is something very simple, but in principle, you can do this also in the infinite dimensional case. And then, of course, you have to be more careful. With the norm corresponding to the norm coming from the inner product on the Hilbert space, satisfying the following. If I take the norm of a composite f after g of two morphisms, then it's smaller or equal than the product of the norms of f and g. And if I take the norm of f star composed with f, or also the other direction, it's the same as the norm of f squared. So here for all composable morphisms and here for all morphisms. And then I call this a star category. And in such a category, one can define and is interested in specific types of morphisms. So let's see, be a C star category. And then we say F, the morphism in C. Then we say that F is called unitary. If it's an isomorphism and its inverse has the same norm as itself. No, sorry, its inverse is the same as its conjugate, so a star acting on F. And F is called Hermitian, or sometimes self-conjugate. And here in the infinite dimensional case, one would have to be a bit more careful, but I don't go into that. If and only if applying star to F, it gives back F. And then one can also define a dagger functor. between dagger categories, so only the first part. In C and D. This is, of course, a functor from C to D, such that if I apply the functor to a morphism and then take the dagger in D, it's the same as F, the star in D, or the dagger in D, and it's the same as F applied to the star of F. All morphisms act in C. And another interesting definition is the notion of a partial isometry, but I leave this out. Instead, I give just one result in this context. And there are many further statements one can make in the context of monoidal categories and braided monoidal categories. And I will try to include a few of them, but maybe for lack of time, I will not say much. Here, this is due to John Baez. And this is not yet in the list, but it will be next time. It says that in a star category, in a C star category, every morphism has what is called a polar decomposition. So that's called F. And then we have F can be written in the form U composed with A, where A, F from X to Y, A is an endomorphism, which is self-adjoint. No, I should say Hermitian. And U from X to Y unitary. And so there are various other analogs of statements we can make about operators in on-purpose spaces. So now we come to section 111. And I had thought that I can finish this today, but probably I will not. This is about adjoints. There will be subsections 112 and 113, but this is the last one, which is standard stuff. 112 and 113 are a little bit more, well, also not extremely deep category theory, but things you would not maybe include in an introduction. But they will be both important in some of the applications that I plan to mention. Now, remember notion of equivalence of categories. So one way to get to, if you have a functor from C to D, to get a functor from D to C, or to consider a functor, is to form an equivalence. So one is the quasi goes to the other, but there is a more general or different notion where you have also functors in two directions. We consider functors, say F from C to D and G from D to C. And then we say that F is left adjoint G, and at the same time, then G is right adjoint to F. And we say they form an adjoint pair of functors by definition, if and only if there are natural transformations which really denoted by epsilon and eta, and call the co-unit and unit of the adjunction, which are natural transformations from the composition F after G to the identity on D, and from the identity on C to G after F, such that for all X in C and Y in D, and from here on for the rest of this part I have to be careful, because in my notes I switched notation, but I try to use the notation I used before, so I have to be a bit careful. We say that the following two morphisms, composite morphisms, are identities. The first one is we start from G of Y. So Y is in D, G of Y is in X. Then we apply the component of eta at the G of Y. So we get from the identity to G after F. So we get G after F after G of Y. But this is by associativity of composition the same as G composed with F composed with G of Y. And then we apply G of the component epsilon of Y, which brings us from F of G, F after G of Y to identity of Y, so to Y. So this will be just G of Y. So we get an endomorphism of G of Y, and we require that it's the identity morphism. And analogously, if we do it in the other possible way, so we start from some f of X, apply F of eta X to get to F after G after F of X. And again, use that this is the same as F after G after F of X. And then we take the component of epsilon at F of X to go back to F of X. So this is the definition, well, actually one definition. We will in a minute get an equivalent other definition. But first some further terminology. So we already said we call epsilon the co-unit. C is hard to see. Co-unit of the adjunction, and eta the unit, and also we use the notation that we say f, and then this symbol. This says f is left adjoint to g, or g is right adjoint to f. Of course, we can also write it the other way around. But since g is the right adjoint, we prefer to write it on the right side. And then assume that we have the situation that f is a left adjoint to g, but it's also a right adjoint. If we would write like that, then we say that this is an ambidextrous adjunction. And also say that f is a two-sided adjoint. It's both the left and the right adjoint. And then, in addition, we use the notation that if G is the right adjoint of F, we write also G F, and then write RA for right adjoint, or F is G LA left adjoint. And then we all use occasionally at least all of those notations and terminology. Now, a proposition. If we have f from C to D and a G from D to C and have an adjunction, so of this type, the G the right adjoint, F the left adjoint, this holds if and only if for every x in C and y in D, there is an isomorphism which I will denote by capital phi xy. This goes from the morphism space in C of x and G of y. Isomorphism to the morphism space in D, f of x and y. Yes, right. And this has the following naturality property. If we are given any morphism f from, say, x prime to x in C, and morphism G from y to y prime in D, and in addition, morphisms which I call phi from f of x to y in D, and psi from x to G of y in C. If we set yeah, this is notation. So we write hom f of f and G from phi. So this we define as the following. We go from f of x prime via f of f to f of x. To via f of phi to, no, I was on the wrong side. Was correct. F of f to f of x. And then via phi to y. And then we can go via g to y prime. And we said hom of f g psi to be so this is a morphism in the space of morphisms from f of x prime to y prime in D. And analogously here, we have the composition. We start from x prime via f, we go to x, and via psi, we go to g of y, and then via g of g, we go to g of x, g of y prime. So this is a morphism from x prime to g of y prime in C. And then the requirement is, and I should have used the space better, we require that the diagram, which I will write down, commutes, where we have here the morphisms in C from x to g of y, and then we can apply phi xy to go to the morphisms in D of f of xy. Or we can use those morphisms here. So here we use the first hom, no, the second hom f g of g of psi. Then we have to get for any psi we have this, so it should be we get taking any psi of this type, we get here to the morphism space still in C between x prime and g of y prime, and analogously here the morphisms in D using hom f of f and g, hom in D from f of x prime y prime, and then here again we have phi now for x prime and y prime, and we require that this commutes. So in other words, these phi's fit together with the possibilities with a natural way via morphisms f and g go from this morphism space to this and respectively.
So it's the same thing of saying that phi xy is kind of natural morphism.
It says that this is a natural isomorphism, but does it say more or not? Maybe not. It's let me see, we have our, well, except except that it's a kind of generalization where phi has two labels. So it's if we fix one of the labels, then we get a match. So in each argument it's natural. But this sum, I'm not completely sure, but it's maybe a little bit more because you can vary both at the same time. And there is I gave some details here of the proof, but maybe I leave it out and only refer to MacLane. Save some time. This is in chapter 4. Yeah, chapter 4. But the idea, maybe the idea is that assume you have these structures here, then you from those you construct isomorphisms between problem C, now not any x, but G of some set. And then here you have the composition of F with G of something. And then you try to get epsilon out of that. And analogously in the other direction, you put here G, X to be G of something, and then from, no, wait, did I say it? No, this was the one we had. Here, Y to be F of something, and construct eta out of it. That's one direction. And in the other direction, assume you have given unit and co-unit, then recover these isomorphisms phi by first acting with F here, then you have F of X and Fg of Y, and you post compose this with the relevant component of the co-unit. Respectively, in the other one, you pre-compose with the relevant component of the unit. And then you get such isomorphism. And then some further comments. First remark. By invoking the Yoneda lemma, you can show that left or right adjoint, if it exists, of course in general it will not exist, but if it exists then it's unique up to natural isomorphism. And therefore, one often talks about the left adjoint or the right adjoint. But there are situations where one has to, if one deals with a family of functors and their adjoints, and one wants to pick particular adjoints, and one has to see or keep in mind how one has done this, and maybe wants also to know what happens if I take an isomorphic one. But keeping track of the isomorphism. And 193 lemma. If no, not if, only if you have a junction, then they form an equivalence between relevant categories C and D, if and only if the natural transformations epsilon and eta in the first definition are not just natural transformations, but natural isomorphisms of functors. Because they didn't just say that F and G are quasi-inverse to each other. In one direction, the other direction. Different. Then some example. Which is nice to know. There are various types of what one calls a forgetful functor. This is a functor from some category which consists of objects having a certain additional structure and then forgets that structure. And the one we consider here, and they are often denoted by U. Actually, I don't know why. Maybe it was just a letter that was used by someone first. So we start from vector spaces and we consider each vector space just as the underlying set. So an extreme amount of forgetting. This has as a left adjoint the following functor. So this is a functor f, which has to go from Z to vector spaces, which takes a Zx and maps it to the vector space with basis x. So each element of the set becomes a basis element, and then we take arbitrary linear combination, and that one also calls the vector space freely generated by the set x. Now, other types of freely generated objects are often obtained by other types of forgetful functors, as left adjoints of other types of forgetful functors, but not every forgetful functor has a left adjoint. And here's an example. Consider the forgetful functor from a category field, where the objects are fields, and morphisms are maps of fields, to again regard the field just as the underlying set. Assume you had a left adjoint. Say F, then we can apply F in particular to a specific, so F from set to field. We can in particular consider the empty set. Then this would have has to be a field. And not just a field, but a field such that, because it should be in the joint, that's the joint, the morphisms in field between K and any other field L have to be isomorphic to the morphisms in sets between what we have here, so the empty set, and the forgetful functor applied to L. For any field L, well, any field L, but this here is just a one element set. There's only one way to, well, in set, remember, the empty set is an initial object. It's the initial object. And that would mean that K is a subfield of any field, and such a thing doesn't exist. Actually, I have not thought more about it. Well, maybe I write this here. K would be a subfield of S, of L, for any field L. Exercise show that what I have described here indeed is a forgetful function, is a vector joint. Of course, I can define that, but I have to do the analogous calculation here and see that things sit together. Another example. The diagonal functor delta we considered this in example 157 as both a left and a right adjoint, and it has the co-product as left adjoint and the product as right adjoint. Concerning forgetful functors, maybe I should have mentioned. I should have this here. That when I look at modules over an algebra, then there is in particular the induction functor from the original category to the categorical modules, which give me induced modules, and this has this is left adjoint to the corresponding forgetful functor. And in the particular case that the algebra is a Frobenius algebra, it's a two-sided adjoint. And we will mention this in detail later on. And
question. So, what is the structure that prevents us from constructing the first joint? So in this case, we have more data in the field category than the vector K category.
Well, it's certainly non-trivial to have such isomorphisms. And in general, I mean, when you have any two functors from C to D and D to C, and look at these morphism spaces or sets in general, then they in full generality they are not related, and that they are actually isomorphic. That is a strong property. Well, actually, it's not, maybe not extremely strong. We will see that under certain conditions we will have left joints and we will have right joints, but having two-sided differences, this is considerably strong. Just, yeah, this fits with the rest. One small remark, which is convenient because it allows me to continue no, it was prime, and it is a functor that is left or right adjoint to a k-linear functor is automatically k-linear again. And this is fine because, as I mentioned, when we talk about linear categories and functors between them, I will usually always assume that the functors are linear. So if taking the adjoint would bring us out of the class of linear functors, then this would be problematic, but it's not. And then a concept that we will need not very often, and originally I had not planned to include it, but it might appear at least once. This was again a non-standard number is not a continuous functor. This is a functor, simply not, well, this is more or less terminology, a functor that reserves arbitrary limits. And analogously, a functor that reserves co-limits is called a co-continuous functor. And we have had a proposition 190, which was a statement about we have already all limits or co-limits if we have particular types of them, and accordingly we have here a lemma that if F reserves products and equalizers, then it preserves all limits, so F is continuous. And analogously or dually, if F preserves all co-products and all co-equalizers, then it's co-continuous. And two simple examples, and then an important statement, which is why this is mentioned in this subsection 111. First of all, the Hom functor from C to Z is for any C continuous. Well, C must admit limits so that this makes sense. And every equivalence of this last thing is not correct. We just preserves those limits which exist. Equivalence of categories is both continuous and co-continuous. And then proposition. Every left adjoint functor is co-continuous, and every right adjoint functor is continuous. Also, over time, but we mentioned this anyhow. When we talked about exact functors, I already announced that there is a connection between exactness and jointness, and we will talk about that. But actually, this we will do in 113, and there is a 112 in between, which is about what is called ends and co-ends, which are particular limits and co-limits, which are important. Okay, thank you for today.